Today we'll be discussing inverse functions. To begin, the inverse of a relation f at x is the relation f inverse of x, in which all the ordered pairs of f at x have been reversed. So, if a, b is an ordered pair in the relation f at x, then b, a is an ordered pair in the relation f inverse of x. So if I have the point 1, 2 in f at x, I will have the point 2, 1 in f inverse of x. So in other words, the domain of f at x is the range of f inverse of x and vice versa. And note that f inverse of x reads as f inverse of x. So in example 1, for the relation y equals f at x below, we want to graph its inverse. So we're going to look at key points that are on the given function graph, and we are going to use those points to graph our inverse. So we see here we have the point -3, 1. So when we go to graph that point, we're going to graph it at 1, -3. So we have that point there. And then our next point that we're going to look at is this point right here at 1, 2. And when we go to graph that, we're going to graph it as 2, 1. And then we look at our next point. The next point that we have here is 1, 4. So now when we go to graph this, we're going to graph it at 4, 1. And then our next point that we are looking at is 2, 5. So when we graph that, it's going to be at 5, 2. And the last point that we have here is at 4, 5. So now that point is going to be graphed at 5, 4. And now we can connect our points there. To have the same form as our graph that we started with. So please note that when we have this function here and we are doing the inverse, it actually is just a reflection about the line y equals x. So we have our line here of y equals x, and you notice that it is a pure reflection about that line. So now, how do we determine the inverse of a relation? If we're given the graph, it's really easy to go ahead and actually just do the opposite points, change our x and y's and graph it. But what if we're actually using a function and it's the equation? How do we go about finding the inverse? So since the inverse is found by switching the x and y's on a graph, that is exactly what is done to find the equation of the inverse. So we have a couple steps here to follow. So your first step is going to replace your f at x with a y in the original equation if necessary. Number 2, you want to switch the x and y's. So then you need to solve for your y. And your last step is to write your final answer using your inverse notation, so your f inverse of x. So example 2, we want to determine the inverse of each relation. So in our first one, we are given a set of ordered pairs, which are points. So we want to do the f inverse of x. So we're going to just go ahead and switch our x and y's in each ordered pair. So it's going to become 5, -2, 9, 3, -6, 0, 4, 1, -1, -8. So that's our final answer there, since it's just an ordered pair. Now in B, we have f at x equals negative 2x minus 5. So step 1. Remember step 1 was to change our f at x to y equals negative 2x minus 5. Second step, we want to go ahead and switch our x and y's. So we're going to do that exactly as I said. X equals negative 2y minus 5. Now in step 3, we want to solve for our y. So we're going to bring over this negative 5, so we have plus 5 equals negative 2y. To get y by itself, divide both sides by negative 2. These are going to cancel out, so we have y equals, I'm going to bring the negative to our numerator. So keep the brackets around our x plus 5 all over 2. And our last and final step here is to write it in terms of our function notation. So our f inverse of x is equal to negative x plus 5 all over 2. And that is our final answer. So now in example 3, we want to restrict the domain of f at x. Okay, well, this is just an example of it. We're not actually going to restrict the domain to begin with. We're just going to actually graph both the function and the inverse of that function. And then we'll talk about why we may want to restrict it. So first we want to graph the function f at x equals x plus 1 squared plus 3. Now, in our lesson before about combining our transformations, we used RST tables. We're going to go ahead and use our RST tables again. So, bear with me here as I write this. So remember our RST, you always start with xy and go RST from outwards to the outsides here. For our function here, our parent function, since you see that we have a squared, we know it's just our parabola, so y equals x squared. So we're going to start with negative 2 and go up to positive 2. So if we sub in negative 2 there, we have 4, 1, 0, 1, 4. Now, this 1 here tells me that it's going to move left 1. So that is a translation that affects our x's. And this 3 here tells me it's going to move up 3. So another translation that is moving our whole function up 3. We don't have any other transformations in this graph. So let's first deal with our x's here. So each x value, you're going to minus 1. So negative 1, minus 1, negative 3, and then negative 2, negative 1, 0, and 1. Now you're going to add 3 to each of your y values. So 4 plus 3 is 7, 1 plus 3 is 4, 3, 4, 7. So those are now going to be your x and y values that you're going to use to graph your function here. So our first one is negative 3, 7, so over 3 up 7. Next point is negative 2, 4, so over 2 up 4. Our next point is negative 1, 3, so over 1 to the left, up 3. Next one, 0, 4, so we don't need to move left or right at all, just up 4. And the last point here is going to be 1, 7, so 1 to the right, up 7. And then we can just connect those points and make sure that we label our graph. So f at x equals x plus 1 squared plus 3. So the next thing that we need to do is we need to actually go ahead and graph our inverse. So remember with our inverse, our x's are now going to become our y's, and our y's are now going to become our x's. So these are now our y's, and these ones here are our x's for our inverse function here. So instead of graphing negative 3, 7, we're going to graph 7, negative 3. And then we're going to graph 4, negative 2. Next point that we're going to graph is 3, negative 1. And then 4, 0. And 7, 1. And then we can connect those points. So as you notice here, we have the same form that we had in our first function. However, the inverse is now taking the parabola and moved it on its side. So now let's go and look at part B, where we need to find the equation of the inverse. So once again, we're going to follow our steps. So our first step is to replace our f at x with y. So it's going to become y equals x plus 1 squared plus 3. Next step, number 2, we're going to replace our x with our y's and our y's with our x's. So x equals y plus 1 squared plus 3. Third step, we're going to solve for y. So we have x minus 3 because we need to isolate our y. So our first step is to get rid of that positive 3. It's equal to y plus 1 squared. Now we need to get rid of that squared. So what do we do to get rid of the squared? We take the square root. Now remember, when you take the square root, it's going to be positive or negative square root of x minus 3 equals our x plus 1. Our last step is to get rid of this positive 1, so we bring it to the left side, and it becomes a negative 1. And then our last step is to write this in our inverse notation here. So f inverse of x is equal to positive or negative x minus 3 minus 1. Now, just to review a couple of the last things about this question, is the inverse of f at x a function? When you look at this, you can perform the vertical line test, and so therefore you get no, it's not a function, because when you draw a line through your inverse function that looks like this, and you go ahead and draw your vertical line, you notice that it hits your function in 2 spots. Therefore, it is not a function. Our next thing, just to note here, in general, the inverse of a quadratic function is not a function. However, you can get it to be a function if you restrict the domain. So if we were to restrict the domain so that x is greater than or equal to negative 1, you'd only focus on the right branch of the parabola. So therefore you'd only have half of it. Similarly, if you were to restrict your other side, you would only be working with the other half. So no matter what you do, if you restrict it one way or the other, then you can have it as a function. So if I were to draw this, I'd have my function like this or my function like this. So I'm creating it so that you don't have the other half of your parabola. So half of the sideways parabola would be a function, but if it's a whole parabola, it's not a function. So there is another example that you can refer to on page 213.